emulsions using integrated membrane technique. Dr. Radwa, please.
Good morning all. My name is Radwa Mourad Taman, PhD Chemical Engineer, GUPCO, Operations Department. Actually, I'm going to talk about my PhD thesis project, but at the same time, I want to take the privilege to take the advantage of this project by applying it in the real petroleum companies all over Egypt, because it's really discussing a very important topic and a very important problem nowadays, which is the oil concentration in the wastewater that is thrown directly in the seawater, and how to make the maximum separation process of these oil traces and prevent it from throwing this water with maximum levels of oil tracing in the seawater that may harm the marine environment. And also to take the advantage of this water to maybe which can be re-injected once again to the wellheads, so that we will gain a complete cycle of this water. So we will have, at the end of the project, we won't have any wastewater further on. This is a typical wellhead, and this is what I have just mentioned, that we want to use the wastewater from the petroleum industry, again to be re-injected to the wellheads, of course, for pressure differences. And that's why we need this water to be very clean and very clear, without TDS, without COD, without BOD levels. And this is the environmental problems nowadays. So that's why we said the problem, that we have oil tracing in the water, more than 15 ppm oil in water. And we have, this water is very high saline water, so that's why we need to make two things. Number one, to decrease the oil concentration and also decrease the TDS of this high saline water in order to throw to the sea or back again to the wellheads. So when I just think about this project at the beginning, I found that if we use the membrane systems, it's very new, innovative technology, and now it's applied nowadays in all over the countries in the global world. So if we find ourselves here in the oil emulsions, which is our problem, so we can use only microfiltration and ultrafiltration as the first stage of treatment. So our aim of the work is just to make two stages of treatment. Number one is that to create microfiltration membranes which can be utilized to decrease the oil concentration, and number two, to innovate or to try to produce RO membranes, which is reverse osmosis membranes, to decrease the salinity of the water, so it can be used elsewhere during the production process. Because we want to decrease it, so in order to, we can decrease the TDS in order to use this water again to the wellheads. Okay, but it still has three problems: the COD, the BOD. So while you are treating the COD and BOD, it can be decreased as well.
I hope we keep this to the end of the session.
Okay.
To bring your chain of thoughts.
Okay. Okay, so at the beginning, as I said, the first stage for the membranes, I use the phase intervention techniques to create the microfiltration membranes, and I mainly use the polyvinylidene fluoride as the main substance for the microfiltration membranes. And what's new is that I use the polyisoanilamine, and I will refer it in my talk today as a PEI, just to be easy to say. with the phase intervention techniques. Okay, so what I want to know in this project is the membrane performance. Is this membrane is really good to treat this oily wastewater or not? So I have to stick for many performance analysis for this membrane, like the oil separation versus each membrane type that I'll use, that permeate flux, and the bacterial removal, which is very important to be applied for the environmental law, which is the law number 4 for the year 1994 for the COD and BOD levels. And also I want to know and I want to test this membrane fouling techniques and this membrane fouling ability. Also, I make some membrane characterizations, like the scanning microscopy, and to see them, and also to see the mechanical properties, tensile and elongation stresses, FTIR, porosity measurements, which is the main important factor we need, because we need to gain small pores at the same time. The number of pores should be higher than the usual membranes, just to prevent the clogging of the membranes at any time, because you are in an oily industry, so that's why you need to focus on the pore size and the pore density. And also the membrane contact angle, to know the membrane hydrophilicity, if it will pass the water or pass the water with the traces, to make sure of that. And the thermal gravimetric analysis, which is the thermal transition temperature of the membranes. Okay, so I made like 5 membranes. I prepared 5 membranes. These 5 membranes, as I said, are differs in the percentage of the PEI, polyisoylenamine, in addition to the basic polymer, the polyvinylidene fluoride. And as we can see here, as I mentioned, for the pore size, we can see that the first membrane was without the adding of the new substance, which is the PEI, the polyisoylenamine. So that's why, as you can see, it has larger pore size. Of course, it will permeate all the solution, all the water, and with all the oil. So that's why we don't need it. And as you see, for the second picture, from the second picture to the 5th one, I use the PEI with different percentage to increase it and to see what's the effect of this new substance on improving the pore size and improving the pore quality of the microfiltration membrane in order to be used in this field. And that's why we can find that the best percentage of the PEI is for membrane number 3, which you can use it for 0.5 weight%. And as I said, this was the explanation of the previous slide. And for the mechanical properties, you will find that, as I said, for M3, for the membrane number 3, which I used for 0.5 weight% polyisoylenamine, it gives us the highest elongation and also the highest tensile strength of this membrane, which is very important to be tested, as I said, as a membrane characterizations. And as I said, this is the membrane porosity and impermeability and contact angle. As we can see here, for the first membrane, without adding this new substance, which is polyisoylenamine, you have the greatest contact angle, which means it will permeate all the solution. But by adding the maximum percentage at M5, as you can see here, you will find the contact angle is 78.3, which means that the PEI increases the hydrophilicity of this membrane and will pass all the water. Okay, and this is for to test the thermal gravimetric analysis. We can find that the glass transition temperature of the prepared membranes decreased from 430 to 410 degrees Celsius, which is not bad, because you will find that the decomposition temperatures results find that when you use the polyisoylenamine, you can reach up to 495 degrees Celsius. For the decomposition temperature strength. And the most important thing that when I used and I test this membranes, the microfiltration membranes, for the oil separations, we found that by using 0.5% PEI, you can reach to 92% separation oil in water. So your water at the beginning of the first stage is totally or most totally free from oil with a percentage 92%. Okay, and for the flux, as I said, it's for the membrane number 3, you can gain like 160 liter per meter square hour in the flux, but you can gain, if you increase the polyethelenamine, like up to 180 liter per meter square hour. But this is for the fifth membrane. But I need to take the average advantage of the pore size with the flux both together. So that's why I chose membrane number 3, not membrane number 5. Okay, and this is the most important thing. As I said, related to the environmental law, you need to lower your COD and BOD levels in the wastewater. So that's why, as you can see here, by the way, I used for these samples a real water from GUPCO fields, real water. So that's why, if you can see here for membrane number 3, it has at the beginning of the COD 12, and then we decreased it. It decreased the COD levels up to 12. It was the feed sample, it's more than 1,000, and the BOD level from 660 to 6 milligram per liter or ppm. And this is why what we wanted to use this new substance or the PEI in the polymeric substance for the membrane technologies. Okay, and the most important factor is the fouling testing. You know, of course, as a membrane phenomena, it can be clogged by any time. But what we want to know is the irreversible ratio. If you have a irreversible ratio, it's very low, so it can be easily cleaned by the backwash or by distilled water. It can be very easily cleaned. So because of course we will face this type of problems of clogging the membranes. But to test this, I make the reversible fouling ratio. It was 23.9 for the first membrane. This is without PI, and 24.6% for membrane number 3, which contains 0.5% PEI, which means that you have a very high degree for the reversible fouling. And this membrane, if it's clogged one day, and of course this will happen, you can easily backwash it with the distilled water. Okay, at this stage, we decrease the levels of oil only, right? So now what we want to gain, we want to gain further treatment is to decrease the TDS of this water. Maybe you cannot use this water to be reinjected in the wellheads. Maybe you can use it in the site and for any facility. So by that you solve many problems. You don't have wastewater again in your field. Yeah. Okay. So by this, we used here new substance, or as usual for the reverse osmosis membranes, I used the main polymer, which is polyether sulfone, with the addition of the new substance, which is zirconium oxide chloride octahydrate, and I will refer it as a ZOH to be easier announced. So I prepared 6 membranes. The first one, of course, without the new substance that should be used, and the first 2 without the cross-linking or the coating for these membranes, because as we will see and as we will know, for the reverse osmosis membranes, we need always the coating layer, this white, to make the cross-linking and to take us out of the range of nanofiltration to go to the reverse osmosis filtration. So that's why we always need cross-linking. So the first 2 without a coating layer, without cross-linking, and I made cross-linking with polyvinyl alcohol, and the other 4 was with cross-linking but with different percentage of ZOH, because that's why I said it's the new substance that I'll use it in the reverse osmosis preparation, reverse osmosis membranes preparation. Okay, and as I said, for number 4, for membrane number 4, it gives me great pore size, small as I want for the reverse osmosis, and also great or higher density for the pores, and as well the size that I want to reach for the reverse osmosis membranes. But as you see here in the membrane number 5, when I increase the percentage of the dead OH to 2% weight percent, what happened is the polymeric solutions started, because they are high viscous solutions, started to make cracks. So that's why they increased the pore size of our membranes, which is not preferable. This was what I said. Okay, and that's why as we see here, membrane number 4 with 1.5 weight percent ZOH is the best reverse osmosis membrane that can be used, which has a great elongation percentage and also a fine tensile strength. Okay, and as we want to know that it's the total pore volume for these membranes, as I said, is for the fourth membrane with 1.5 weight percent ZOH is the best one to be used, because it has the best pore density that we want to use for this purpose in treating the oily water. Okay, and for the contact angle, as we mentioned, for the first two, of course, they are very permeable, water permeable, because there is no coating. And when it goes down, of course, the permeability will decrease. And as we can see here, also the fourth membrane and the fifth membrane gives us the great contact angle, which can be used to permeate the water and also at the same time to hinder the passing the traces, which is like the remaining traces for the TDS that we have. And as I see that the performance is the most important thing for the membranes. So I just tested these membranes with making synthetic solutions of this water, and also the last concentration was what I used the water for 130,000 TDS, and as I said, because I used the real field water from GUPCO fields. So as we can see here, the salt rejection give us results, good results, up to 92%, especially for the last orange category, which is the real field water. After the first stage microfiltration, and then you can gain the salt separation up to 92% for this real field water. Okay, and this is for the permeate flux. Of course, as I said, the first two membranes will give us great permeate flux. Why? Because there are no coating, or without using the PVA coating. But this is not what I want. I just want the coating to increase the pore size or pore density. So it also gives us, for the membrane number 3 or membrane number 4, moderate flux. And as you will see here also, we make testing for the long-term membrane testing. Yes, 2 minutes, okay. For the long-term membrane testing, to see what's the ability of this membrane to stand out with us in the industrial process without being clogging easily. Okay. And the conclusions that for the microfiltration membranes, it's advisable to use the new substance, which is the PEI polyethelenamine, in this trend of membranes for the manufacture of the microfiltration membranes of this type, with the addition of polyvinylidene fluoride. And as I said, the best percentage for the PEI is 0.5 weight percent. And we achieved from this stage up to 92%, up to 95% oil and water separation, and we can also get the highest permeate flux, which is 180 liter per meter square hour. Also for the bacteria removal, we proved that for this microfiltration techniques, the usage of the PEI decreases the COD and BOD in the passing water, and this is what we want to achieve. Okay, and the same, I'll go fast in this because I just wanted to let you see the real membrane samples in the lab, which is the microfiltration membranes and RO membranes. And what is very important is that I transferred this thesis project to a real project, and I hope inshallah it will take place, that can be used in all the petroleum companies, inshallah, in the future. So by just adding very little or very less amount of the carbon filter, so you can just make the first stage of screening, and after that you can use the whole process as I mentioned. But what you are going to see is that you will have to use the high pressure pump. And I have made the solution for this. If you want to change the usage of this high pressure pump, you can use the forward osmosis membranes, which is very, very new or recently applied here in Egypt. You can use the forward osmosis membranes instead of the reverse osmosis membranes to get rid out of the high pressure pump that can make problems in the site. So by that, you can find that you have the initial concentration of the oil in water at the beginning in this oily wastewater was 85% ppm, and you reach the final stage down here to 0 ppm, zero concentration of oil and grease in the water. And this, as I said, was tested on the real field water. So, and also by the TDS, you decrease the TDS from 130,000 ppm to 5,000 ppm, which can be used in any other facility, or if you can make it re-injected again to the wellheads. And as I said, for the COD and BOD, they are decreased from 1,900 up to 0 respectively, 0 ppm respectively. Okay. Thank you.
Thank you very much, Dr. Thank you very much, Dr. Radwa, for this nice tour among the ultrafiltration, nanofiltration, and the RO membrane. Now it's time for questions. I ask you, to start with the question who didn't finish, with the gentleman had a question, and after, yes, في سؤال عندك؟ كمل يلا. يعني sorry, يعني ladies first, يعني. And after Dr. Radwa, if there are any other questions to Mr. Alexander and Mr. Muhammad Sami, they are welcome.
Yeah, thank you for your presentation. It's very good. But first, it's better to use this water again to be injected to the well. But my question here, why you should remove TDS? Okay, for oil you should remove the oil, correct. But for TDS, this is slightly bit strange for me, because you put anti-scaling and re-inject it again to the well. That's our normal procedures in that matter.
This is a way that you can use the water, as you said, that you can use anti-scaling and use any water for the wellhead. This is, of course, this is great and right. But if you want to throw this water in the sea water levels, you cannot throw it with 40,000 or more than 40,000. This is according to the environmental laws. It should be up to 5,000 ppm. This is the right way to throw out or get rid from this water. But as I said, if you don't want to be exposed to throw this water totally in the seawater and gain the discharge or the zero discharge loop, so you can use this low TDS water for any further facility in your production facilities. So that's why I decreased the concentration of the TDS to 5,000. It can be either thrown to the seawater, or it can be further treated and can be used in other facility during the production facility that you have.
Actually, sometimes we make it re-injected on the ground, underground.
Yeah.
The reservoir water well underground. So this is another technology we are following on. Thank you.
Okay, you're welcome. I don't know the specs. I'm not sure from the specs for the steam regeneration, but I think if you just lower the TDS from 130,000 TDS to 5,000 TDS, so you can do any further treatment with this water again. Maybe you can increase the units of the reverse osmosis, or as I said, for the forward osmosis. As you increase this treatment units, you can lower the TDS, so it can be used for the steam generation.
It's a very, very interesting subject. The reason I'm saying this question, because typically in a remote gas plants where we have large CO2 removal units, we always need water for makeup.
Yeah.
Okay, and it's rare to have this water in this remote location with a very low concentration of TDS.
Yeah.
So it was very difficult for us to find a source of water. If this can be used as an alternative source for water, this would be great.
Yes, inshallah, and the most important thing is that it decreases also the bacteria level in this water, so you will not have or not face any other problems that is related or raised from the higher COD levels or BOD levels that are in this water.
Okay.
Actually, this is good for ballast water, for example, to remove the oil before throwing into the sea. Concerning normal brackish water, nanofiltration technology is already applied, and the National Research Center have developed nanofiltration membranes in a system to deal with different qualities of brackish water in the Nile Delta or in the desert, and they have appropriate membranes or appropriate systems for each composition of brackish water. But the oil, I think, it's very interesting for the ballast water particularly. I agree with you that re-injection, you don't need to remove many things, but maybe some things ought to be removed, as she said. That's why.
Because it will solve the most important problem is that the wastewater in the seawater. So that's why we need to get a good qualifications of this water if we were gonna throw it. If not, we can make it further treatment by lowering the TDS again and can use it any elsewhere.
Thank you. Any other question to Dr. Radwa? In that case, we will thank Dr. Radwa and invite other questions to who want to be asked first?
If you allow me, Doctor, I need to emphasize what the gentleman from UB said, that it is technically or economically feasible to go for a very high conversion. This was my point to stress more on it, because I need to know if this is really installed or not. So.
Okay, so the question is there a commercially proven technology that converted high sulfur fuel oil into distillates? So we had a unit in Canada in 1990, started up in 1990, and it ran for 15 years. It was a smaller unit, but at that time it ran at high conversion. And our latest design, Uniflex, like the configuration I showed for the customer in China, starting up next year. This is designed for 97% conversion. And we've licensed 7 units, all starting up next few years. So after this one in China, there is another one in Europe in 2022. So to answer your question, yes, UB has technology that can convert fuel oil to 97+ conversion. Yeah.
Thank you. A question for Mr. Alexander. Hussein, have you been satisfied with the
It's a basic question in the subject itself. I can understand that the motivation is to convert high impurities crude to available finished products. It's a stability. It's difficult to convert crude to petrochemical. So my question is it easier to convert methane to petrochemical? Which way is easier in economics and everything? I can see the methane can be cracked to other petrochemical products. Why the concentration now is moving towards the conversion of the crude heavy liquid to these products? Is it easier to convert methane, for example, because we have plenty of gases? So this is my basic question.
It is what it means that here we had in the petrochemicals industry, we say gas to olefins or gas to polymers and so on. Now it's relatively new, the crude to polymers directly. Of course, this is because of the added value and the demand for natural gas for clean, as a clean fuel purpose application. Yeah. But do you have to add something, Mr. Alexander?
It's more a matter of economics. Your distillate has a great value as diesel. And your VR is cheap product. It can be wasted product. The incentive is on the feedstock prices to convert the crude to highly valuable products. And that's why the crude to chemical is so important, because the crude is cheap. And again, it's always about a global economic balance. You just ask for maximum conversion, but what if lower conversion can be more valuable if your UCO has a high value? Today we have a project, we work on a project where UCO can be valued as low sulfur fuel oil. So in this case, high conversion is not anymore the target. It's the optimized conversion which is the target, where the hydrogen conversion, your investment, and the final product you're producing is balanced to maximize your economics, your global economics. And it's a case-by-case scenario. That's why there's a lot of studies, and we have performed great tools to study these things.
This is also has been done for the sour crude, or this is only for the sweet crudes, this recovery units?
It is possible also with sour crudes. Not all of them. You get levels and limitations, because you cannot remove all the sulfur with residue hydro conversion. But however, you will need what we call diluent. You will still need diluent to make low sulfur fuel oil. It's a blending there, according to the available fluid in your refinery.
Thank you.
Thank you.
Well, on behalf of the audience and the society, we thank our distinguished speakers. Unfortunately, Dr. Reem,
unfortunately, Mr. Stefan Joubert couldn't make it due to travel obstacles. And we are closing this session now, and the next session will be chaired by His Excellency Engineer Osama Kamal and Engineer Tamer Heika, which will start momentarily.
My question to Mr. Alexander and Mr. Tamer, you are the both converted for all catalysts. I am from SOBC, and I have delay cooker to change to
Uniflex or H-oil, was the difference between the two units and the comparison between hydrogen consumption, the catalyst cycle lifetime, and the percent of the product, and how we can chill to the severe condition to make flexible to the mold for middle distillate or petrochemicals. Thank you.
I suggest we have this in private conversation.